So let's go through STP operations. STP operations. So attention, please. Attention. So with STP operations, using STA, it stands for spanning tree algorithm. So STP, it builds loop-free topology. Loop-free topology in 4 steps. 1, to elect the root bridge, which is the reference point. Then elect what we call the root ports. Now the root ports, these are the ports that communicate to the root, communicates to the root bridge. Then elect the designated ports. These are the ports that communicates from the root bridge. So we have the ones that are pointing to the root bridge, and then the ones that are pointing away from the root bridge. And then lastly, elect the alternate or the blocked port. So during STA and STP functions, switches use what we call BPDUs, bridge protocol data units, to share information about themselves and their connection. So in that process, when switch 1 and switch 2 connected together, they have to communicate together. They are connected together and they have to communicate together. So by default, STP is enabled, okay? And now they have to agree among themselves which one is going to be the center. Without your information, for you can go there and you interject and like, oh, I want this switch to be the root bridge. But by default, they can communicate together and decide which one is going to be the root bridge. And those are the steps that they need to go through using that message, and the message is the bridge protocol data units, to share information about themselves and their connection. So BPDUs are used to elect the root bridge, then the root port, the designated port, and alternate port. So each BPDU contains what we call bridge ID. Each BPDU contains a bridge ID. So that identifies which switch sends the BPDU. So every time a switch sends, it has to have the BPDU that it sends, it contains an ID. The message that I send, I have to include my ID, the IDs. So the bridge ID. So the bridge ID involves in making many of STA decisions, including root bridge and then the port roles. Now, when it comes to the port roles, these are port roles: root ports, designated ports, and then the alternate ports. These are the port roles. These are the port roles. For example, if I have a switch connected to this, and then this, then maybe this here, like this. This is the root bridge. So the ports on the root bridge, because these ports here, they are the one that communicates away, or that points away from the root bridge. So these are designated ports. And then the one that communicates back to the root bridge, those are the root ports. Here are root ports. This is a root port. And then now here, this link here, it's the one that is going to be treated as the redundant link. So the redundant link, one end, it has to be designated port because it's communicating away. It can't be a root port. And another concept that you need to note is that every switch, even if, let's say, it's connected to many switches. For example, let's assume that, this is our switch. At this side we have a switch, this side we have, okay, like this, that this is the root bridge. We have this other one, maybe even this. You see, all these are switches, but this is the root bridge. Okay, so the port that connects to the root, that points to the root bridge, it's the one that we're going to, or that is going to have the root port role. But these other ones, are they pointing to the root bridge? Yes, because our root bridge is this. So are these other ports pointing to the root bridge? No. So all these ones, please, they are designated ports. Designated ports, designated ports. So what does this mean? That every switch, it has to have just a single root port. Single root port. This port that communicates to the root port. Now, if in case, let's say you have another one, if you have another one, then you are likely to have the loops on the network. Because we need a single root through our entire switched network. And if you have 100 switches, for us we expect one single root. The moment you have the second one, then you are likely to have the loops on the network. Okay. Each PPDU contains this, and then it involves in, as you can see, root bridge and then root roll, port roll, sorry, not root roll. So the bridge ID contains the bridge ID. So a bridge ID is just a container. So that container contains priority value, the MAC address of the switch, and the extended system identifier. So the lowest bridge ID value is determined by the combination of these three. The lowest bridge ID, it is bridge ID value is determined by the combination of the three. So by default, all our switches, that the extended ID and priority ID, they're the same. So it will be 3,003, I think it's 32,768, something like this. That is the priority value for all. Priority value for all switches. By default, still all switches by default, they have one as extended system ID from the VLAN. Because now the VLAN switch, by default it has VLAN 1. So the 1, it is from that VLAN, default VLAN. But in case you create the other VLANs, then automatically things are going to change. Instead of use the instances, you have VLAN 1, you have instance of 1, VLAN 10, the instance of 10, I'll show you. Then they are combined now, the extended system ID, and then this they are combined. So most of the time you will see bridge ID as 32,769, but the default saying that it is 8. So a 1, it comes just from the system ID, and then it is added here to make it 9. Yeah? So they are here. As you can see, the bridge priority, it is here. The default, it is this. Then ranging from 0, it's from 0 up to this. So if you are to deal out to change this in an increment of, you see this, that in an increment. So it's from 0 up to 61,440. So if you want to change, to play around with this figure here, priority value, if it's 0, the next one, it will be with the increment of this, 4096. If you want the next one, it will be this plus this. You get it? Not you to add the 1 here. But you have to add this, so with an increment of this. So extended system ID value is a decimal value added to the bridge priority value in bridge ID to identify the VLAN. The VLAN is for identifying the VLAN. So if you have these other VLANs, you've created the new VLANs, then we expect other value than we want, maybe 10, maybe 30, depending on the value, the ID that you've used. Then MAC address. When two switches are configured with the same priority, as you can see, we said all the switches, they have to have, by default, the bridge the priority should be the same, 32,000, and the VLAN 1. So meaning that there is a match, there is a tie. So to break a tie, the MAC address, it will come into play. Okay, if you're one, if you're maybe you're Leonard, I'm also called Leonard. Please, Leonard, not Ronald. Are unique. Actually, the two are the same here. Actually, all the switches, all of them, just go home and try it out and see. They're the same. VLAN 1, priority 32,000, but the MAC address different. So here we are, elect root bridge. Elect root bridge. I think I need to summarize this with a practical, otherwise we are not going to do the practical. But when you look at what we have here, we have the priority 32, this is 24, meaning that this one here, it is less. This, are you seeing this? Because this is 24,000, but this is 32,000. This is 32,000. Then automatically this is the root bridge. Okay? But in scenarios where all of them, they are 32, 32, 32, 32. Now, we have to go to the MAC address. Look at the MAC address. We have 22 here. I'm not sure of this, but when you compare, you start from left, okay, going to the right side. So compare and you see this one by one. One by one. For example, if I have, let's assume that here I have 0, A, what? Okay. 2, 2, 2, this is 0, maybe B, then maybe 4, 4, 4. Then this one here we have 0, maybe what now? And use 1, and then this is 5, 5, 5. So when you're comparing, start from left. This is a 0, compare it with this. Compare it with this. It's the same, isn't it? Let's go to the next. This is work for, I think it's P4 work. No, P4, P2. Arranging orders in, sorry, words in alphabetical order. P2. P2. So we are actually trying to arrange our MAC addresses in ascending order. That's now here it's 0, 0, 0. Now let's go to the next. This is A. This is 1, and this is B. Which one is the least? Which one is the smallest? Is 1. Then how about A and B? Which one is the smallest? It is A. So automatically here, if you are looking for the root bridge in this scenario, it will be this root bridge. And then now this one here, since you are saying that this is the least compared to this and this, then this one here is going to be the backup. Okay? The backup. That in case this one here is down, then this one here is going to play as the root bridge. So the impact of default, default. That if you are dealing with the default, because now here I'm saying the impact of default, and yet we have meaning that we're not going to see the impact of default, because this one here it is less. It's not the same. We're supposed to have all of them, and then you see the impact of default. That if all the root, this priority, the priority and extended that are the same, what is going to happen? You consider this. Okay. So in the previous year where we have this, as you can see, the root bridge, it's this one here where we have the 3 but the priority is lesser. But here, here where we have the default, we have to go with, oh, but still, I think they were supposed to put a different figure. And when you look at this and see all of them, this one here, it's the one with the least MAC address, and then it takes us the root bridge. But this, it's the same as the previous one. No? It's the same as the previous one, so it doesn't make sense. Yes, please.
What is the data format for the MAC address?
The
data format.
But it's there. Look at it. Look at it. Anyway, you will see that in your class. You see that in your class. Because the length of the MAC address, it totals to 48. And the 48, it has to have 12 hexadecimals. 12 hexadecimals. They can be grouped as a byte. They can be grouped as a byte, or the byte we expect to divide. We expect something like A, B, then you space. Okay, or you can have there are 12. There are 12. You can have actually, I think, 4. Yeah, maybe B, C, this. So there will be 3. 2 bytes, and then 2 bytes. So if the 2 bytes here, they're equivalent to 16 bits like this. So if you add this, it gives you 48. You will see the format anytime, but there are 2. You can use some 2 hexadecimal value AB with this, or AB, I think with a dot, or the ABC D, then with this dot here. Separate. You will see those formats. It depends even on the device, but there are 3 formats that I know. So impact of default BID, you will not see this unless maybe if you do your own personal readings, that where all information is the same. It's 132,000, 132,000, 132,000. And then if it's the same, you consider all this. In the previous one, as you can see, that elect the root bridge, but we have this as the lower priority. So if the priority is least, then automatically it's the one to take over. Determine the root pass cost. The root pass cost. There are those scenarios where to tell that this is a redundant link, but which end should be blocked? You have to look at the distance. Which one has the longer distance than the other one? The one with least distance, that is the cost. Cost is the distance. So the one with least cost, least distance from that port to the root bridge, it's the one that is going to be a designated port. Designated port. Then the other one, which is longer, then automatically that one is going to be pressed in alternate state, be blocked. That is the system. But to do that, it is not all about you using your naked eyes and you see from this point to the other point, it is longer than this. You might find that the distance from here to the other one by physical, it is shorter. But when it comes to the speed of the port, it's gigabit, maybe it's fast Ethernet and the distance is shorter. But the other one that you're calling longer, when it comes to the speed, it's like a GB. It's GB. Okay? I can give an example when it comes to actually bring on board is that what you see as the best route because of the distance, maybe when it comes to the capacity, each one to the speed, it's fast Ethernet. But the one you are seeing physical as long route, for it the speed, it is actually the speed, it is maybe 1 GB. So this is the table. Where the port is operating in fast duplex, of course it's 10 MB per second. And imagine you're downloading a movie of maybe 1 GB. It will tell you need 2 days. You need 2 days, you're downloading something. 10, the link speed, if it's 10, now with this one here, for 10, look at this, that for 10, the cost is 100. That even if the switch is here, then to this point, it's operated, the speed it is 10 MB per second. So the cost, the distance, it's 100. Now, if you have fast Ethernet to the other side on the other link, the fast Ethernet, it supports 100 MB per second. So the cost is 19. So that cost, that link that has 19, if it's from here maybe to the other corner, and then this one, it's just close. That route it's not going to be used. It's not going to be used. Why would you decide to drive in the road that I've explained? Because it is maybe colder, maybe it is. Yeah, you can decide that, let me stay in jam other than driving that road. Because you're going to go through that road and then tomorrow go to the garage. To the service. There, you'd rather park in the jam, turn off the engine, and sleep. There's a time when I slept in the jam. Actually, I was in a taxi, I was not driving. So, I was in a 10 MBs, the distance it's 100. 100 MBs, the distance it's 19. Where we have 1 GB, the distance is 4. Where we have 10 GB, that if the port supports 10 GB, then the distance is 2. Okay? The distance is the 2. But as you go maybe in these other capacities, you'll find that the distance is the same. The speed is the same. Where the speed is the same, the cost is also somewhat the same. And then actually you can do, because this one here, it works with the ports, not the entire switch. It has to be done on a port. Meaning that the cost where we have a 2 here, you can adjust this. Let's say you're trying to adjust. Okay? The default route to take you to 1 degree, but like, you're not driving, you're not riding. Why are you using the main gate? There is another. You say that another route. You can go through this small gate. So if you don't want to use the main settings here, you can adjust the costing so that it is treated as something that is long. Okay. Now we have 19, you can adjust this to have the figure, the value that is higher than this. But you cannot force this to have 18. You can force this to have 19. This to have 19. But the 19 you cannot force it to have. So our main route is this by default, but you want it to be this. So you adjust, you make sure that the other one, the cost is changed to higher. Let's assume that this is 19, the other one is 4, but you want this one of 19. What are you going to do? Give this one the 20, so that it is treated as something that is too long. Get it? And then the 19, now it takes the preferred choice. So when you look at this still we have this trying to show us the cost. Yeah, though it's not clear, and then the root, the port roles. So once you have a topology, you should be able to actually identify the port role, then the switch roles, and like this is the root bridge, and then this is maybe the backup, and then the root ports. Because if it's a root bridge here, then the connected ports, these are designated. Then the one that points to root bridge, those ones are root ports. See? And then the redundant link now aside, one end it has to have to be the designated port, and then the other end it has to be alternate port. Now in scenario where we have two links on this, we have this and then this one here. So this, and you want to decide the distance, to look at the distance and block that. So from this switch here to this, I think this to this, the pass it's 19. Here, the pass it's 19. But when it comes to this, as you can see, to go through switches, through two switches, now we have this as 19 and then 19, meaning that this route here, the cost is 30. It's 36. 36, 38. The other one it's 19, so it's 38 from here through this, like this, to this switch. But here it is 19. 19. But still you can change this now that if you want to communicate, that all these computers, if that communicate with this one here, to go through this, still you can do that. If you make this a root bridge, this, then automatically the communication, they have to go through this. But if you make this a root bridge, this, then automatically, why should it go through this, and yet the distance here is only 19 to go through 36. So the internal root pass cost, is equal to the sum of all port costs, the sum of all port costs along the path to the root bridge. So as shown in the figure, path with the lowest cost becomes the preferred, and all other redundant paths are blocked. So in an example, internal root path cost from switch 2 to the root bridge, which is switch 1 over pass 1 is 19, while the internal root pass cost over pass 2 is 38, because pass 1 has the lowest overall pass cost to the root bridge. It is the preferred pass. And F1 becomes the root port, the F1, which is this one here. Now here we are saying it's the preferred route because of this switch 1, it is the root bridge. Okay, but in case let's say this was the root bridge, then automatically this it would be the best route, because still it would be 19 to reach because the target, as you're doing the calculations, summing up the cost, you sum up to the root bridge. Now if this was the root bridge, then to reach the root bridge using this pass 1, still it would be 38. Am I communicating or I'm preaching?